Hey, and welcome to another live coding. Today we will be doing the age prediction model again, where we are going to do a regression model based on images of people and try to figure out how old they are. So let's jump straight into it. All right. Well, actually, before we look at PerceptiLabs and start working there, let's take a quick look at the dataset. And if you watched the previous live coding, this will be a little bit of a repetition, but just to cover it. So this is how the dataset looks like. It's going to be a CSV file, like it's the standard in PerceptiLabs now. And then we will have a folder of a bunch of images, like normal. And the images look like this. It's from 0 age all the way up to 110, which is impressively old. So everything there, and the ages are inside the file names. It's I believe it's the age, it's the ethnicity, I believe, and then or gender, and then ethnicity, and date it was taken. We'll link to the dataset in this video when it comes out, so you guys can look and reproduce it. But the two important parts for us is going to be the age and of course the image. Then we have the CSV file, which looks something like this. So very simply, I constructed it by listing all the images and with a little script, and just extracted the first digits as the age. And then we got this CSV file, which will be the one which we're reading into PerceptiLabs. All right, so with that covered, let's jump into PerceptiLabs. Now, first thing we're going to do is just create a model. Nothing surprising there. And I'm running on our cloud, so we have a bunch of data sets already loaded here. But this is the one we're interested in. And we're going to set this one as input, this one as output. This will very soon be renamed as target instead, as it really is the target, it's not really the output of the model. And then we'll have images as the type for the first one, and numerical for the second one. Since we're not classifying them based on age, we're instead trying to predict what age they are. And we want to randomize the partition because, as you saw in the CSV file, it is very ordered. If we don't randomize the partition, we're going to get the 10% of testing is probably going to be everyone at age 90. So we won't train on any of those cases. So we're just randomizing it. And these are training settings. We'll come back to those. We won't run the model straight away, so they'll pop up again. Okay, so here's our recommended model. I haven't actually tried running this model on this dataset. It may work, it may not work. I think the model is a little bit too small for it to work well. So what we're instead going to do is use a model which I know will work decently, at least as a start. And then we can try experimenting from there. And the model we're going to use then is a model based on ResNet. So we're going to use the pre-trained layer ResNet 50 here. And as you see in the settings here, we have the include top as no, which means the 3 last layers of this ResNet are removed. And that leaves us up to replacing those 3 last layers with our own. And the trick here is that, one, this layer is not, or this model rather, is not trainable. Meaning it will only do inference, it will only do feature extraction. And it's a bit of a shortcut for us just to get some good features out of the images straight away. And the second important part is that it has weights preloaded into it, which supports the case that we can get features of the images extracted straight away. So the only thing we need to do then is to add these 3 new layers, and they're going to be dense layers. That's how ResNet looks like. It's a bunch of convolutional layers and then 3 dense layers at the end. Those are the 3 dense layers which have been cut off from this one. I'm sure you could try expanding on convolutional layers as well, but I don't know how well that would work. So we'll just plop down 3 dense layers and start adjusting those settings. So for the first one, this one's going to crash because the output needs to be 1 here. That will be fixed soon. But for the first one, we want 512 neurons. And if you're asking where I came up with that number, it's something which worked before. I'm sure if you try, you can probably try a few different variations of that and it will still work pretty well. The important thing here is you can't go too low. It is still a decently complex task, so we want some amount of complexity in the model. Then we go down a little bit to 16 before we finally go down to 1, making this one almost act like a bridge. And the last output is important. We have no activation function. And the reason for that is, well, I guess you could have ReLU as activation function. It would essentially be the same, or close to. You can't really use sigmoid because sigmoid goes between -1 and 1, meaning you can never reach the digits of 100, which we need for some cases. And for the other ones, we're using ReLU, as that is a very standard and efficient activation function. I think that's everything we need to do. That's the entire model. So when we have our ResNet model ready, we just run, and we'll get to set all of these. So for epochs, we'll set it just to 4 or 5. Batch size we can leave the same. It is a decently sized dataset, so 32 shouldn't be too large. The loss function, quadratic, again, we want to do regression. And everything else looks good. So let's start running. So it'll take a little bit for it to start visualizing anything, but as soon as it does, we'll start seeing some interesting things. There we go. All right, so great first picture. Let's jump into, this, if you're not familiar with this dashboard compared to your old one, it's split up a little bit different. We can look at that first. You'll notice you have a global tab, which will be your global losses. And in this case, you only have one output component. The idea is that later on, you'll be able to have multiple output components, meaning for multiple individual losses, and one combined global loss. That's the end goal of this new setup. But then we also have output 1 and input 1, which are directly these components, where input 1, of course, you can press here and view it. We'll get more statistics into the input 1 later on, or into the top tab of input later on. But the output is the more interesting one. So in output, we can see a few things. We can partially see accuracy, which is somewhat irrelevant for this case. Accuracy, this one is another one which will be replaced soon by some more appropriate metric for regression. Accuracy right now is just if the 2 digits are the same, you'll get a 1. And I think, I mean, it's 2 floats, so they're never going to be truly the same, but if they are the same int, at least, convert to the same int, it will be the same, or it will be a 1. So ignore these 2 for now. The interesting ones here are the prediction versus ground truth, to see about how right we're hitting. And then the loss. So the loss in this case will almost represent our accuracy. Since the loss is quadratic, if we square root this loss, we will get the distance between the correct answer and the predicted answer. So the loss will be a very nice way for us to track how far away from the ground truth we are with our predictions. As a very simple example, if the loss is 9, we are free. We're what's called free ages, free numbers away from the correct prediction. To summarize, we want the loss to go down. Nothing miraculous there. And it looks like it is going down, so that's good. One thing I haven't done with this model, which I usually do, is to jump on and take a look at the gradient. Hey Looker, hope you're doing well. Nice that you could join. And the important part with the gradients is, of course, that they're non-zero, which they seem to be. But also, that's not gradients. But we probably also want them to have this behavior where they start pretty large and then grow smaller and smaller. That way, you know that the model starts converging rather than fluctuating between different values. So I did a test run on this model before, and it took about 4 to 5 epochs for it to reach a decent loss. We're still at a fairly high one at 100 from last one, 50 now, which I don't know what the square root of that is in my head, but it's still a fairly large difference between that and where we want it to be. It would be awesome to get it down to about 10 digits or below 10 even. We can also see that the validation stays about the same, even though the training loss is going down, which is an indication to maybe we're overfitting a little bit. We might need to add some dropout into here to make it work better. So that's something else we can try. If we manage to get this loss down, we'll jump back into modeling and get some dropout going on the dense layers. Although the training is taking just a little bit longer than I would have hoped. I got a question if we will start the age prediction model from scratch or continue from the last one. Well, if you're just joining, you join pretty much at the same point where the last one stopped. So that's perfect timing. We just before this went over building the age prediction as well as the data set. So we already covered what we did in the last video. And this time it is not crashing, which I'm very happy about. Turns out to have been some GPU issue with the recording software. All right, I think we can stop this model. I wouldn't be, the gradients still look good. The loss is still diminishing, as we can see. It's almost halving every time, which is perfect. The thing which is not perfect is the validation. So let's try to do something about that. Let's try to add some dropout to it and see if we can get the validation to have a similar curve as the training. And we don't really need to wait for the results since we can see them right here. Got another question if it's possible to use the GPU model on Mac. That's a good question. Last time I checked, TensorFlow did not play too nice with anything but NVIDIA GPUs. I think it depends a lot on what GPU you have on the Mac, but it might work. It's worth a try. CUDA and CUDNN is not too difficult to install. And the PerceptiLabs answer to that, I suppose, is if it works for TensorFlow, it works for us. All right, so let's add some dropout to this depends layer. And do we not have the fix here? Okay, let's try adding some other. All right, so this might not have worked as I wish. Since we need to do a hotfix for dense layers and the dropout, I thought that was in this version. All right, let's ignore adding dropout. Let's try a custom built model instead. So the main point of this one was to use the ResNet as a feature extractor, but let's try training everything from scratch ourselves instead. So if we want to do a stacked CNN, for example, we can do a simple 2 or 3 CNNs and then ending with 2 dense layers. And just seeing how that one's going to act. Recommendations for catch-up. This video contains everything the last video did, Gautama. So if you just, and I think this one will be out about a week from now. So if you wanna catch up on anything, that you can just catch this video when it comes up in about a week. I also think that you have the possibility to rewind this stream to when it started. So that might work as well. Also, if you have any specific questions about anything you encounter, feel free to just ask them either now or jump on the Slack. All right, so I'm just building out a stacked CNN, and I'm not really doing anything special more than just using some best practices of doubling the feature maps, and then putting in some random value for the dense layer. We're going to want to reload on these ones as well. That looks very creepy. Right, let's see. I think the activation function everywhere is right. And this is the fun part of neural network, or deep learning, I mean. So let's try it out and see what happens. This one should run a lot faster than the other model. Even though the pre-trained models are only inference, meaning they don't actually train anything, they seem to be quite a lot slower, just because they're so large. All right, so important first point. Do we have gradients? Yes. we just had huge ones at the start, which is fine. And now we have more reasonable ones, but still fairly large compared to what we had before. Second, how is the loss looking? Pretty good so far. It's definitely starting out worse, almost twice as bad as the ResNet. But again, it's to expected. We're training from scratch rather than using a pre-trained model. So let's see how this one looks like after about 4 epochs. Note that this one does not seem to have the same issue with overfitting, although it might be too early. Never mind, it might have. It's probably too early to tell since we never got to the point where it got a decent training. Now, if I'm not mistaken, dropout might not work on the dense layers. I'm pretty sure it works on the convolution layers. So let's try some dropout on that instead. Can try something like that and see how that works. And I think the picture is just getting creepier. Alright, let's run this, and let's run for a few more epochs as well. 5 seemed a little bit short when we were training from scratch. Okay. Gradient's looking fine. Hopefully this won't be any worse than the last one. That's a huge loss. So the main point we're going to see a difference here is when we are a few epochs in. Scratch that, it definitely did get worse. Maybe we had a little bit too much dropout. Yeah, loss at 1,500 is definitely worse than the 100 we had before. While this one is training, I'm also gonna dig up the data set we had. I'll post it in the channel for anyone who's interested of testing it as well. Another question is, why did the current version of PerceptiLabs only have a few data types compared to past where NumPy arrays and even environments? Now it has only images and 1 number per row. We did a little bit of restructuring with the data ingestion. And the reason for that was to have it a bit more guided. It's the NumPy format was very free-floating, whatever the wording is. And it was often difficult to get it into the right format. A CSV file is very transparent on how it's looking and how it should look like. We currently do only have a few data types, as you're saying, but the formats which we're using currently, which recommends models based on different data types, can expand really quickly. Data pipelines are not very difficult to add to the tool, so you'll very soon be seeing arrays, time series texts, which wasn't even in the old one properly. And it will very soon surpass the old one. The only thing you will not see in the new one anytime soon is environments, unfortunately. But that we also realized that having, as cool as it is to having environments, focusing on both reinforcement learning and the image field and the generative field, and trying to cover them all at the same time, it was difficult to keep up with the training layers, which is why, if you try this one, we'll see quite a lot of training performance in the training compared to the old one. It's a lot more optimized. All right, this model did not work great. Let's remove the dropout from the last layer and maybe put the dropout on this one to 0.9. And try running that one instead. It would be very cool to get a model which performs similarly. I guess this model without dropout performed in the ballpark of what the ResNet did. But it would be cool to get one that outperforms it even. We'll see if this one can do that. Okay, and let's see. Well, this one is training. Can go over to gradient and go over to loss, which will be the two interesting ones. Much better. All right, let's see if that one decreases now over time. And in the meantime, we have the data set here. Let's double check so it's the correct one. Yeah. So there we go. If anyone's interested in data set, you should now have it in the chat. And I can quickly show it as well while this one is training. This is the website we got it from. And as you can see, there's a bunch of images here, and it's split up so it has the age, the gender, and the race as the three different categories with the date and time, if that would be interesting as well. Let's get back to the model. Tip is you can use the scroll wheel to zoom into any graph you want to inspect a little bit closer. Currently, whenever new data comes in, though, it updates it. Should probably do something about that for it. But even though this model did get better over time, it's still not really close to the neither the one without dropout nor the ResNet model. Yeah, and the validation here stays the same as well. I think the trick would have been to use the ResNet model, which we used first, or this one actually, and then add a little bit of dropout to the dense layers. I wouldn't be surprised if that worked quite a lot better. The dense layer work a little bit, as far as I've seen, at least, work a bit more reliable with dropout than normal convolution layers. So we'll get a hotfix for that, and then you guys can try that out as well. But for now, I think that's where we will end it. So to summarize, a stacked CNN performed in the ballpark of the ResNet, but the ResNet got to better performance much quicker since it is pre-trained, and it does help a lot with the feature extraction. The thing which we were constantly struggling on though was the overfitting, and the way to tackle, or one way to tackle overfitting is with well, two good ways actually. One is with adding dropout to add more robustness to the model, and as a regularization method, it essentially tries, it's like trying a bunch of models in parallel and summarizing them. It is an intuitive way of seeing it. And each of those models you're trying is obviously, since neurons have been dropped out, smaller than the original model. The other way is to just reduce the model size. Overfitting often happens because well, as the name implies, you're fitting the solution curve, or what's a good name for it? Essentially the decision plane, I believe, decision line, whatever you want to call it. You're fitting it too well to the data set. And one way to reduce that is, of course, to have a less complex model which has a less complex decision line, and therefore doesn't overfit as much. But I hope you guys enjoyed it. It's great having you here, and as always, hit me up in Slack or on our forum if you have any questions. But have a great day, and take care, everyone. Bye.